just finished thinking about and exploring how the release of protons from certain compounds during dissociation leads to solutions of various pHs. During those discussions, we relied heavily on the observation that some acids ionize with great efficiency in solution, while others ionize only slightly in an equilibrium process governed by the constant Ka. The smaller the Ka value for an acid, the less dissociation that takes place, and therefore, the weaker the pH of a resulting solution of that material. But we never really stopped and asked the question, what causes this? Why is there a difference in the ease with which various acids ionize? Why should hydrochloric acid dissociate almost completely, while acetic acid releases only about 1 proton for every 10,000 dissolved molecules? Now, to answer this question, we'll have to invoke electronegativity, molecular geometry, hybridization of orbitals, covalent bonding, and a host of other concepts from our previous lectures. But it all really boils down to 2 simple questions. First, how much charge is on the atom bonded to the acidic hydrogen? And second, how stable is the conjugate base of that acid? This lecture promises to be a very rewarding one indeed, as we begin to reach back into the body of knowledge that we've accumulated in the first half of the course and begin applying it to new concepts. Let's get started. It stands to reason that the first stop on our discussion of how easily acids dissociate is to consider just how stable an acid molecule is. Humphrey Davy got us started on this by correctly identifying hydrogen as the critical element for acidity. A compound must have a hydrogen that it's willing to let go of as a hydrogen ion if it's to meet the Bronsted-Lowry definition of an acid. So, what does it mean to release a hydrogen ion from a molecule? Well, it means that the electrons from the bond to the hydrogen need to be taken on completely by the other bonded atom. This results in a full positive charge on the hydrogen, a full negative charge increase on the conjugate base, and of course, the separation of the two into solution. So if breaking the bond means completely separating the charge, we can think of polar bonds as being already on their way to breaking in this kind of process. In other words, more polar bonds to hydrogen should mean stronger acids. In some sense, this notion works. Just consider hydrochloric acid, one of our 6 strong acids from earlier in the course. Now, chlorine, with its high electronegativity, pulls the bonding electrons closer to it, even when bonded to hydrogen. Chlorine wants those electrons, and it wants them badly. So as soon as hydrochloric acid hits water, the proton is released. As a very general rule, we can use the polarity of the bond to the acidic hydrogen to gauge the strength of some acids. Here's how. Now, in theory, any compound that has a hydrogen could be thought of as an acid. So let's think about a few very simple compounds that have hydrogen, some of which we think of as being acids and some of which we sometimes don't. So here are 4 different potential binary acids. We're going to think about HF, H2O or water, NH3 or ammonia, and CH4, which is methane. Now, in order for these to behave as acids, what has to happen, right, from a Bronsted-Lowry sense? Well, in order for them to behave as Bronsted-Lowry acids, they've got to lose their hydrogen in the form of a proton. Now, what does that mean for hydrofluoric acid, HF? What that means is that the proton release results in the fluorine taking on a negative charge, right? That's something that fluorine's not so bad at. In the case of water, release of one of those hydrogens as a proton means that we have to get a negative charge onto the oxygen. Another familiar species, hydroxide, we see this quite a bit. Ammonia. Now, for ammonia to act as an acid, it's got to lose the proton, and now that negative charge has to go onto a nitrogen. And finally, in the case of methane, when we remove a proton, we now have to put a negative charge onto the carbon. Now, knowing what we do about periodic trends and electronegativities, which of these seems like the most likely scenario to have happen? Right, of course, putting a negative charge on a fluorine is actually doing it a favor. This is the most electronegative element that there is. So fluorine tolerates it very well and creates a very stable conjugate base. Now, if we think about hydroxide, that's also not too bad, right? Oxygen, with its electronegativity of about 3.5, that's not too shabby either. It's pretty good at taking those electrons on without a fight. But as we continue down our column here, we're really going across the row in the periodic table in terms of which atom we're dealing with as our second atom in the binary acid. So when we think about things like ammonia and methane, we're putting the negative charge on progressively less electronegative atoms, to the point at which, when we really think carefully about the electronegativity of carbon compared to hydrogen, it's not different enough to make any difference whatsoever. And what that means is the equilibria here are affected. Exactly how they're affected is this way. HF is going to be the strongest acid because it has the most stable conjugate base. And methane at the other extreme is actually not even considered an acid at all, really, because the process of removing this proton is so terribly disfavored that its pKa comes in somewhere around 50. Now, from a practical perspective, that really means that methane is not acidic at all, that ammonia is only very, very slightly acidic, if acidic at all, by a standard definition. And water, of course, and hydrofluoric acid, we know actually, can release their protons enough to really be important in chemistry. So as we work our way left to right across any given row of the periodic table, we can observe this trend of increasing acidity in binary acids as bond polarity increases. Indeed, the trend holds perfectly within our row. As we work our way across rows of the periodic table, binary acids become increasingly stronger, since each step to the right takes us to a more electronegative bonding partner for the acidic hydrogen. This helps us to explain why hydrocarbons have essentially no acidic character at all, why deprotonation of ammonia is rarely even considered a real possibility in chemistry, why water's ionization, though significant, is very small, and yet hydrofluoric acid is strong enough that it can etch glass. It may seem a little bit strange that in our quest to understand acid strength, we often have to analyze the structure of its conjugate base. This, however, is an overriding tenet of thermodynamics. For any equilibrium process, proton transfer included, the free energy, or stability, of the products is every bit as important as the free energy, or stability, of the reactants. So we have to be wary of the possibility that there will be additional considerations involving the conjugate bases of certain acids. And this may counteract the instability introduced by more polar bonds to the acidic hydrogen. In fact, this is such an important consideration that it's going to dominate the next unit of this lecture. In our first example of the lecture, we were able to overlook the conjugate base behavior because the effect of the bond dipoles was the dominant factor. This was true as we considered binary acids in a given row of the table. Yet, a simple change to our investigation will quickly unravel that method. Consider another form of binary acids, the hydrohalogens: hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. If we consider this series of binary acids using elements not in a given row, but in a given group, something changes. Even though the dipole of HF is the greatest, it's actually the weakest acid. Even though the dipole of HI is the weakest of all, it's the strongest acid, beating out HBr by a slight but meaningful margin. This flies directly in the face of our method of using bond dipoles to assess acidity. Shouldn't this trend be reversed? So what's going on? Well, there must be a more influential force behind the trend in acidity for binary acids as we move down a column of the periodic table like the halogens. Now, if you think back to our discussion on periodic trends, you might remember something about this. As we progress down a row of the periodic table, electronegativity does indeed decrease, but the size of atoms and ions increases dramatically. This is because we're adding new valence shells to their electron clouds. Now, this increase in volume means that chlorine can disperse a negative charge over a greater volume than fluorine can. Neither of these can stack up to bromine's ability to distribute that charge. And iodine, with its valence shell in the 5th energy level, is the undisputed king of charge distribution within that group. So even the mighty hydrogen-fluorine dipole was not enough to compensate for the fact that larger halide ions like chloride, bromide, and iodide distribute charge more effectively over a greater volume. In order to exist, fluoride ion has to pack that negative charge into a little 2nd energy level valence shell, and that charge density is its undoing. So as a general statement, when comparing binary acids of similar structure, we can make the assertion that conjugate bases with better charge distribution are responsible for stronger acids. And this trend holds in many cases for other weak acids whose conjugate bases bear localized negative charges. Take the example of water, H2O. Compare this to dihydrogen sulfide, H2S, and H2SE, H2TE. Right? The very acids used to debunk Lavoisier's theory that oxygen is the essence of acidity. Now, we see a very similar trend to the halogens, don't we? Decreasing pKa values as we move down the periodic table. This is because the resulting conjugate bases require that a negative charge reside on the group 6 element. Oxygen, being the smallest of these elements, can only distribute this charge over a very small volume. Sulfur, selenium, and tellurium, however, have increasingly larger and larger electron clouds around which they can distribute the charge. And this increases the overall stability of the hydrogen sulfide, hydrogen selenide, and hydrogen telluride ions. The object lesson here? When it comes to conjugate base stability, size often matters. All other factors considered equal, the larger, more polarizable conjugate bases will have stronger conjugate acid counterparts. Now, most simple binary acids, like the hydrogen halides that we've investigated so far, don't contain oxygen. As I mentioned previously, some of them were actually first cited as arguments against Lavoisier's postulate that oxygen was the essence of acidity. So what drove Lavoisier to advocate his now disproven theory that oxygen is the essence of acidity, a claim that lives on only in the name of this familiar element? When he made it, his attention was focused on yet another trend in acidities of a series of compounds known as oxyacids. Oxyacids are a bit more complex than binary acids. They're a class of chemical compounds that contain an OH bond chemically bonded to another central atom. Now, don't confuse this with the OH- hydroxide ion from Arrhenius's base definition. Here, we're talking about an OH motif covalently bonded to at least one other atom. Now, we're actually already very familiar with this type of acid. Nitric, sulfuric have all made appearances previously, and all of them fall into this class of compound. But there are other oxyacids that we have not yet discussed. Acids like nitrous acid, sulfurous acid are based on combinations of the same types of atoms. Now, notice that every last one of these oxyacids has at least one acidic proton bonded to an oxygen. This means that the oxygen will be taking on a negative charge when the acid dissociates. So the effective conjugate base size and polarizability has been essentially removed in this group. Now take a close look at the pKa values for these acids. And consider the first acid dissociation of each. Do you see a trend? Sure. Nitric acid is stronger than nitrous. Sulfuric is stronger than sulfurous. Decreasing the number of oxygens bound to the central atom correlates with decreased acidity of that compound. This is no coincidence. Other oxyacids follow the exact same trend. A classic example of this is the oxyacids of chlorine: perchloric, chloric, chlorous, and hypochlorous acids. Now, hydrochloric acid clearly doesn't belong in this group because the acidic hydrogen on HCl is attached to the chlorine. Here instead, the acidic hydrogen is bonded to an oxygen atom. Now, within this group of oxyacids, as the amount of oxygen decreases, sure enough, their pKa's increase, reflecting the same decrease in acidity that we saw in our previous example. So now it's easy to see how Lavoisier might have reached his erroneous conclusion about oxygen and its relationship with acidity. As you can see, in all of these examples we've looked at so far, the addition of more oxygen atoms increases the intrinsic acidity of each class of oxyacid. But if oxygen isn't the fundamental source of acidity, why does it seem to bolster the strength of these acids when its ratio in them is increased? The answer to that lies in oxygen's potent electronegativity, 3.5 on the Pauling scale, just about the highest of all elements, second only to fluorine. Consider our chlorine-containing oxyacids once more. Hypochlorous acid has but one oxygen bonded to the chlorine atom. Now, what is the consequence of this arrangement of atoms? Of course, the oxygen is going to pull the electron cloud of that chlorine atom, creating a mild charge separation that makes chlorine a bit more positive and oxygen a bit more negative. So this oxygen is reluctant to release a proton, which would cause an even greater buildup of negative charge, right where the negative charge from the bond dipole already exists. Hypochlorous acid is a weak acid with a pKa of about 7.5. That is more than 10,000 times weaker than acetic acid or vinegar. Now, add another oxygen to make it chlorous acid. Something changes. That second oxygen is pulling the other direction against its sibling on the other side of the chlorine. This gives the chlorine an even greater positive charge. The increased positive charge on the chlorine makes it pull against the oxygen containing the acidic proton even more. And it begins to win the tug of war. So now the oxygen bearing the acidic proton is losing some of that negative charge density that made it so reluctant to release its proton in the first place. And the pKa of chlorous acid reflects this at about 1.9. That's more than 100,000 times as acidic as hypochlorous acid, all caused by one oxygen. Now, add another oxygen to make chloric acid, and yet another to make perchloric acid. And the effect is amplified each time, creating acids with pKa values of -1 and about -10, respectively. In fact, both of these would be considered strong acids by rule because their pKa values are negative, meaning that practically every molecule in a sample of these acids would be ionized in solution. Another way to think of this is again to consider the stability of the conjugate bases that form. With each progressive addition of oxygen, the conjugate bases of these oxyacids have less and less localized negative charge. It's instead distributed over progressively more and more chlorine-oxygen bond dipoles. And, as we already know, distributing charge leads to greater stability. Unfortunately for Lavoisier, at the time he had no way of knowing that the true nature of oxygen was not to act as an acid itself, but to function as an electron withdrawer in oxyacids, weakening the acidic oxygen's hold on the true source of acidity, its hydrogen. So we've seen how electronegativity and atom size can profoundly affect the stability of a conjugate base in binary acids. We also took a look at the role of oxygen in oxyacids and saw how the presence of more oxygen atoms around a central atom weakens the OH bond, increasing acidity. But there's yet another factor to consider when trying to explain the observed ionization constants for some acids. And this one takes us back to the concept of conjugate base stability. Our last factor to consider is resonance. And we discussed quite a while back how Heisenberg's revelations about electron mobility in molecules led Linus Pauling, Gilbert Lewis, and others to rethink the nature of chemical bonding. Remember that electrons like their freedom. They want to move through larger volumes of space, and that means that more resonance means more stability, not only in neutral molecules, but in ions as well. By now, you can probably guess where I'm going with this. All other things being equal, conjugate bases with greater resonance delocalization of their negative charge must therefore be more stable. Invoking resonance allows us to explain why compounds like formic acid and methanol have such drastically different acidities, even though on casual observation they seem so similar to one another. So here are formic acid and methanol. Now notice formic acid has a second oxygen bonded up here to its central carbon, but otherwise these molecules look as though they're very much of the same ilk. But that extra oxygen up there, we're going to find in a moment, adds a very interesting dimension to the conjugate base of this particular acid. So when we deprotonate a formic acid molecule, what do we get? Well, we get what we always get on deprotonation, of course, an hydrogen ion. But we also get the corresponding conjugate base, in which the negative charge is on the oxygen that initially was bearing that acidic hydrogen. Exactly what we expect there. Now, let's consider instead methanol. When methanol loses its proton, well, we also get a conjugate base with a negative charge on the oxygen that was bearing the proton. So far, identical behaviors. So why is it that their acidities are so different? The reason that their acidities are so different is this. If I make a duplicate of my conjugate base of formic acid, I can, simply by shifting electrons around, create a second resonance contributor to the overall resonance hybrid for that conjugate base. All I have to do is move my electrons here down off of my negatively charged oxygen and then back up onto that second oxygen that's the difference in the two structures. So that means that I have a resonance contributor with a negative charge on this oxygen in the conjugate base and a resonance contributor with a negative charge on the oxygen in this version of the conjugate base. So what does that tell us about the resonance hybrid? Well, it tells us that the charge is distributed over those two atoms. And when we combine these two resonance structures to form a new resonance hybrid, what we find is that indeed we have only a partial negative charge on each oxygen. That charge is now distributed without breaking any other rules like the octet rule or any other rules associated with Lewis structures. But now turn your attention to methanol. Its conjugate base, known as methoxide, has nowhere to go. I can't move this negative charge down because as soon as I attempt to move the lone pair down into the carbon-oxygen bond, there's nowhere for any other electrons to go to get out of the way. I would have a carbon that would have a grand total of 10 valence electrons. That's not allowed by the octet rule. And in order to alleviate that, I would have to break a bond, right? Because there are no pi bonds left to move as we had up here. When I go to the tables and look up the pKa values of these two acids so that I can compare their intrinsic acidities, what I see is that formic acid has a pKa of somewhere around 4, whereas methanol has a pKa somewhere around 16. That's 12 orders of magnitude difference in their equilibrium constants, their Ka values. So what this tells me is that the resonance stabilization of the conjugate base in formic acid has a tremendous effect on its relative acidity when compared to methanol, which has no resonance stabilization in its conjugate base. In short, this effect cannot be neglected when it's present. So, true to our earlier assertion that conjugate base stability matters, the inclusion of just a bit of resonance stabilization in a conjugate base can have a profound influence on the acidity of a compound. So, today we finished our discussion of acids and bases by asking if it's possible to predict the acidity of a compound in the absence of all but its chemical structure. We started with binary acids and found that the fundamental prerequisite for an acidic compound was a hydrogen bonded to an electronegative atom. But then we recognized that the stabilizing effect of size in the conjugate bases for these simple binary acids trumped all other factors, making hydrogen iodide the king of binary acids with a pKa lower than any other. Then we considered binary acids of similar size with different atoms bonded to the acidic hydrogen. We used the example of ammonia, water, and hydrofluoric acid. We determined that within the row of the periodic table, those acids with more electronegative atoms bearing the acidic hydrogen will be more acidic. Next, we went on to consider oxyacids, a class of acids in which an acidic OH motif is bonded to a central atom. We used the examples of oxyacids containing nitrogen, sulfur, phosphorus, and chlorine as central atoms, and we used them to illustrate the trend in which additional oxygen atoms increase the formal charge on the central atom, pulling more and more electron density away from the acidic OH. And this, of course, forces the oxygen to relinquish its hold on the acidic hydrogen more easily. We even took a moment to finally forgive Lavoisier for misnaming one of the most abundant elements in the universe. Finally, we considered the effects of resonance on acidity. We compared formic acid's resonance-stabilized conjugate base to that of a similar compound, methanol. And when we did, we saw that a tremendous increase in acidity was attributable to the resonance in the carboxylate anion that forms when formic acid is deprotonated. We've covered a huge slice of one of the most fundamental but more important chemical reactions known to man, proton transfer reactions, and the materials that participate in them, acids and bases. But our focus lectures on acid-base chemistry are at a close. Don't dismay, though. These compounds and this chemistry will appear again and again as we move on to study additional fundamental topics on our way to understanding how it all works. Next up, we're going to give protons a well-deserved break and instead turn our attention to the transfer of electrons in chemical processes. Electrochemistry is next. Let's test our understanding of how structures of molecules affect their acidity using challenge problem. Let's arrange the following compounds in order of increasing acidity or decreasing pKa based upon their structures in our analysis of them. Here are our 5 compounds: acetic acid, ethane, ethanol, hydrogen iodide, and trifluoroacetic acid, with their molecular formulas beneath. But remember, if we want to really analyze their acidity, we have to think about their structures, not just their formula. So let's put those structures up now. Now, what is it that makes a molecule acidic? Well, it has to have a hydrogen that it's willing to release as a proton. And if you look at all of these compounds, you'll notice that there's one in particular that doesn't really fit the bill. Right? So if we're going to organize these in order of acidity, let's first ask ourselves, do they have an acidic proton at all? And in this case, we see an acidic proton on TFA, trifluoroacetic acid. We see one on HI. We see one connected to the oxygen here on ethanol. And we see one over here on acetic acid that's also bonded to an oxygen. But look at the molecule ethane. There is no real polar bond to a hydrogen. In other words, there really isn't any bond here that would be willing to release any one of these hydrogens as a proton. So ethane is essentially considered to be neutral, not even an acid. But if we were going to classify it as an acid, it would be an incredibly weak one. Now, let's look at the other end of the spectrum here, because we have another low-hanging piece of fruit here, and that's HI. Remember, hydrogen iodide is one of our strong acids. It ionizes completely when we put it into solution. So we know hydrogen iodide is going to have to be the most acidic compound by virtue of it being on the strong acid list. But that leaves 3 more that we have to organize: acetic acid, ethanol, and trifluoroacetic acid. So let's start by analyzing conjugate base stability and using that as our metric for acid strength. When I deprotonate acetic acid, I get a resonance effect which delocalizes that negative charge across the 2 oxygen atoms. So I have negative charge here, but it's not very concentrated negative charge. Let's look at the conjugate base of ethanol. When we remove that proton, we get an oxygen that bears a full negative charge. There's nowhere for this charge to go. So it's a denser, stronger negative charge. And remember, the buildup of charge in general is not favorable. And finally, we have trifluoroacetic acid, which will behave much like acetic acid does, having this resonance-stabilized conjugate base. So let's put ethanol in its place as the second weakest of the acids. But that leaves us with 2 more: acetic acid and trifluoroacetic acid. Both have acidic hydrogens, both have a very similar looking resonance-stabilized conjugate base. So what makes the difference here? Well, what makes the difference here is these fluorine atoms being very, very electronegative, which means they are going to pull electron density away from the acidic side of trifluoroacetic acid, creating a larger, stronger dipole within the molecule, which means that it's more likely to lose this proton in an attempt to mitigate some of that positive charge that's already building up as a result of the fluorines. What that means is that acetic acid will be our 3rd weakest acid, and TFA will be second only to hydrogen iodide in acid strength. So using a series of analyses of various structures, we were able to rank all of these compounds in terms of how acidic they are.